My name is Giampaolo Carosi. I go by GP. I'm a research scientist here at Lawrence Livermore National Laboratory. We're located about 40 minutes east of Oakland in the Bay Area. We are primarily a national defense lab, but we do a lot of fundamental science as well. And I'll show a couple of overviews here on what exactly we do. I primarily work on dark matter research. I have experiments that try to look for dark matter that we know exists, but we just don't know what it is. And so that's what primarily I spend my day job on. Sometimes I dabble around in superconducting qubits for quantum computing, which is a lot of fun. But for now, I'm going to start with a intro of Livermore, and then we'll talk about the Science Slam format that everyone else will do. So I'm going to share my screen real quick and make sure everybody can see it okay. Can folks see this? Let's see if it goes to full screen here. Everybody good? All right, so here's where Lawrence Livermore is. For those of you in the Bay Area, if you're driving on 580, going to I-5 like you're going to go to Southern California, we are right in Livermore, California. It was established in the 1950s. We're basically 1 square mile of really awesome laboratory space. We have a ton of facilities, a fairly large budget, 2.8 billion with about 8,000 employees. It's a very large enterprise, and we do a ton of science. I've been here about 16 years, and I'm constantly surprised every day. We also have an experimental test site way out towards Tracy, which they do a lot of really cool kind of explosives work as well. And they have a lot of open area there to do stuff. So what is a national lab? So a lot of you may have heard of national labs, but maybe not know exactly what they are. Livermore is just one of 17 labs that are run by the Department of Energy. And this is just an overall list of them, and they kind of run the gamut from pure science, pure fundamental research, to more technology, like Sandia is more of an engineering lab where they're focused on, getting it to work and getting it into the field. And so there's a ton of them in the Bay Area. We have SLAC, the Stanford Linear Accelerator, which is where SAGE started. And then there's Berkeley Lab up on the hill by UC Berkeley. And so these are the 3 labs locally in the Bay Area, and then there's ones all over the U.S. And here you go. Here's the full map of some of the main Department of Energy labs. There's also other labs from like NIST, for example, is a Department of Commerce lab. But these are the primary Department of Energy labs. And what do we do? So some of the real reason for national labs is to do what they call kind of big science, things that you have to do at a huge scale that university programs wouldn't really be able to do, and it is further thinking than maybe what industry would want to do. And here's just two examples of one of our high-profile programs. One is Sierra. This is high-performance computing. This is a massive computer. This is right now it's the number 3 on the top 500 list of supercomputers in the world. Another example is the National Ignition Facility. This is an amazing site where they use 192 laser beams to try and compress a single pellet of hydrogen to create basically a mini star. They're trying to basically cause a small thermonuclear explosion right there to do all kinds of studies of high energy density science, and maybe one day even fusion power. And they're getting closer and closer to that every day. So there's a huge kind of core, these are just what we call our core competencies. We do a lot of stuff with, as I mentioned, high energy density science, which is lasers, compressing things. There's some really cool advances in manufacturing, think 3D printing, but like beyond just the little plastic things you have here, like actually making new materials by getting to the fundamentals of how materials are made. Bioscience, bioengineering, there's been a lot of work actually, especially recently, given by COVID, people have done a lot of work. I work in the nuclear and chemical section, so we do a lot of nuclear forensics and others, laser and optics, and there's a huge amount of work that's done on earth and atmospheric science as well. And all of this is being supported by the high performance computing and the simulations and data sciences. So this is just kind of a quick whirlwind tour of Lawrence Livermore. If you want to know more information, check out our Wikipedia page. Feel free to jump on llnl.gov. And you can find out all kinds of information. We have internships and all kinds of fun things going on. So I don't want to take up too much time. I just wanted to give a quick overview of what we're going to be doing this morning. So I have 4 wonderful speakers that have kindly volunteered to give what they call a science slam talk. So a science slam talk is essentially an elevator pitch. Usually you have a very short amount of time to explain to somebody, especially, on the street or anywhere, what you're doing. And it's really challenging because there's so many nuances and details that you have to get into to really explain your science. So the challenge is, how can you break it down very simply, but still get your main points across? And so the idea is that we're trying to basically get people interested. So the way we're going to format this is I'm going to call on each of the 4 speakers. They're going to give their kind of 3-minute slam talk. And then afterwards, we'll open up for about 5 minutes or so if people have questions specifically on that talk. Just, questions you have on, is there a concept you didn't quite understand? Where can you learn more information? Can you explain this one concept again? That kind of thing. And so once we've gone through all 4 of them, we'll open it up to a kind of round table, and there we'll kind of discuss more general stuff and have hopefully an open conversation. Since we have a ton of people online right now, I think the easiest thing is we're going to probably mute everybody with the speakers for now, because you always get that one random person that has their lawnmower on. And if you have a question, either put it directly in the chat. Joanna's kindly offered to monitor the chat, or raise your hand, and we'll try to call on folks and unmute them as they raise their hand. So with that, let's go ahead and start with the first speaker. So the first speaker is Becca Walton. So Becca is a postdoctoral researcher in the materials engineering groups here at Livermore. She currently lives in Pleasanton, but grew up in Northern Virginia, and went to college in Pennsylvania. She went to Penn State for a bachelor and did a PhD in material science there as well. And in her free time, she enjoys doing glass blowing, pottery throwing, and playing video games. So with that, Becca, go ahead and share your screen and kick us off. And you're still muted, but so you need to get, there we go.
There you go. Can you hear me okay?
Sound good?
Awesome. Thanks for the introduction, GP. Without further ado.
Yeah, I don't think we're hearing the audio, but if there's any music, but that's probably all right.
Oh, now it's not advancing. There we go. Space. The final frontier. Now, we don't have starships just yet, but what we do have are satellite-based telescopes. Hypothetically, such telescopes could allow numerous researchers to peer into the unknown. However, in practice, access to such telescopes is fairly limited. This is due in part to the difficulty of manufacturing the mirror components necessary for light capture and focusing. These mirrors have to be perfectly polished, stiff, and lightweight enough to be launched into space. And as such, the way that we currently make them is costly, time-intensive, and highly specialized. These are all areas that I'm aiming to address with my research. To do this, I'm leveraging the flexibility of 3D printing. Now, 3D printing is probably a far cry from what many of us think of when we think of, say, glass blowing, which uses a long metal blowpipe to form molten glass. My process is decidedly less dramatic, but it does offer some impressive advantages in terms of geometric flexibility and dimensional fidelity. I've developed a UV-active glass resin formulation, which can be printed and cured in much the same way as traditional plastic 3D printing. Because this resin can be printed and cured at the same time, I've also been able to use it to make shapes that have previously been too complex or too thin to make with other methods of glass 3D printing. Once printed, I can thermally process these shapes and turn them into a transparent glass. Because this glass can be polished to a very smooth surface finish, is very stiff and also doesn't expand or contract too much when we heat it or cool it, it's an ideal material for application in space technologies. To demonstrate the robustness of this printing process, I've been working on printing a couple different test structures, which notably includes some of the largest glass that's been 3D printed at Livermore National Lab to date. To begin, I've mostly been focusing on structures that are fairly similar to what we currently use in space satellite technology. However, one of the most exciting aspects of 3D printing is that we can use it to make shapes that we can't currently make with other forming methods. To this end, with this project, we have plans to combine stress simulations, which will approximate the lifetime of one of these satellite mirrors, and then we can intelligently design a mirror and support that will perform better than those traditionally in use today. This flexibility, the inherent accessibility of 3D printing, and the elimination of a lot of these costly machining steps means we can envision a bright future for these 3D printed optics. In a world where more scientists have access to satellite technology, we'll be able to boldly see what no one has seen before.
Very nice. Thank you, Becca. So let's open it up for questions. I want to give people enough space if they want to put something in the chat, or if they want to open, raise their hand. I guess while people are thinking, I did have one question for you, Becca. How hot do you have to make your resin? I have a crummy, plastic 3D printer here. I know they have to bring it up to a pretty high temperature, but glass is pretty hot, right?
Yeah, so the cool thing about this resin is that I do it at room temperature.
Oh, wow.
So it's mostly made up of different plastics and different organic solvents. So I do all the printing at room temperature, freeze it in place with that UV light, and then the next time it needs to see heat is when I start to dry it and thermally process it to take away all of those organic components.
Nice. Okay, it looks like we have one question in the chat from Sierra. Do you want to unmute and ask? Or I'm happy to also read it. Maybe I'll just read the questions to make it easier for folks. So Sierra Howard asks, I don't quite understand how the mirror is used on the satellite. Can you clarify how it helps the telescopes?
Yeah, sure thing. So the mirror is one of the components in the telescope that redirects the light coming in towards all of the focusing and light collection elements that then turn that into the image that we get.
Oh, nice. Okay. Another nice question here from Helena. Could this 3D printer be used in space to quickly replace a broken mirror like on the ISS?
Yeah, so that is something that we're really interested in for 3D printing. For glass 3D printing specifically, it's a little bit more difficult because you do need these fairly sophisticated furnaces that go up to very high temperatures in order to get these mirrors out the other end. But in the future, when we can also send those types of furnaces up into space, it would be a great way to do those kinds of fixes because you can make it on the fly.
Very cool. I have a question from Amani, and I apologize if I mispronounced that. Has the mirror been sent to space yet?
That's another not yet, but we are talking with some of our sponsors, and they have interest in doing it. We just need to get them the samples that will work for it. So fingers crossed soon.
And then Angelina asks, how long did it take you to come up with the 3D printing process?
Oh, a while. So 3D printing of glass has been being worked on here at Lawrence Livermore National Lab since I think about 2015, if I'm not mistaken. So I am honestly fairly new to it. I started in about 2020. My current process, it took me about a year to get it working to an okay point. And now that I've been working on it for close to 2 years, we're getting it to like a good place. And that's a pretty standard timeline for developing a process like this.
Cool. So Angelina also asks, did you have to go through any trial and error process?
Oh, so much trial and error. So much of science is trying something that you really think is going to work, and then it just catastrophically not working. So that is a big part of what I do every day. It's I try something, I think it's going to make this process better. Let's say changing what type of glass I have in my resin, and then on the other end, it turns into something terrible, and I have to figure out why and how to make sure that doesn't happen next time.
Nice. Mani also asks, what inspired you to come up with this alternative?
So kind of the limitations of the previous process. So the previous iteration of glass 3D printing didn't use this UV light. So it was basically just depending on the ink, to kind of, you know how like when you squeeze out toothpaste and it just kind of stays in place on the toothbrush, it was just depending on the ink to do that. So that didn't create the strongest printed structures. So we were thinking like, okay, how can we make stronger printed structures that can allow us to make these more complex shapes? And we kind of looked to another area of 3D printing, which is called stereolithography, which sounds like a big scary word, but it's basically just when you have that big vat of plastic that you can shine a UV light on and cure layers consistently. So if you've ever seen like the Eiffel Tower being pulled up out of that big vat of purple liquid, it's that. So we're like, okay, if we can combine that capability with this other type of 3D printing, then we can get something really cool.
Very cool. So Parasha asked a related question. How long did it take you to develop that kind of resin?
Oh, it's still in development for sure. So that resin was developed over the course of a 6-month internship to get it to like a usable place. And then a lot of my focus for the past year and a half has been making that resin really good. So in these types of applications, you're rarely done with something. You're always kind of working on it to see how much better you can make it.
Very nice. And then Swamaya, and apologize that I mispronounced that, asked what could cause damage to the mirror in space, and if so, how would you fix it?
So there's a couple different things. One is particulates getting into the mirror and kind of roughing up the surface. So then it's not going to reflect light as well, right? Another thing that could break it is we see these really big temperature swings in space. So we choose materials that will inherently not respond to temperature as dramatically as some other choices, but there is always the possibility for failure when you experience those big temperature swings. So that can cause cracking in mirrors. And right now, how we fix that is we have to bring the entire satellite back down a lot of the time to fix it, or we have to send a very specialized team up to fix it. So harkening back to one of those other questions, if we can figure out how to 3D print these things already up in space, that's a much easier fix than doing either of those things.
Of course. So I'm going to ask 2 more questions, and then we'll move on to the next speaker. Savannah asks, did your hobby for glassblowing lead you to want to take up this project?
Oh yeah, definitely. My PhD was in ceramic science, so it's something else I really love, also something related to one of my hobbies. But I've always had this passion for glass. It's just, it's so cool. It does things that no other material does, and you really get to see that in glass blowing. So it was always also one of my professional aspirations to get into glass science as well.
Very nice. And then the last question from Swamaya, how are these mirrors tested before launch?
Yeah, so we've got a lot of basically compression testing that's done. So these mirrors have to be strong enough to stand up to stress. So we basically try and squish them and see how much force it takes to break that mirror. And then we also do a lot of reflection testing. So making sure that surface is as smooth as we think it is so that we don't get any aberrations when we then send it up. And then we also do temperature cycling testing to make sure that it can stand up to those extreme swings in temperature that I talked about before.
Great. Thank you so much. Appreciate that.
Yeah, thank you, everyone. Those are great questions.
We're going to move on to the next speaker now. So the next speaker is Felicia Sutanto. So Felicia graduated from the University of Michigan and received her PhD in nuclear engineering and radiological sciences back in 2021, so recently, and is working as a postdoc on, she worked on fast neutron measurements for anti-neutrino detectors called Watchboy, and the construction of a near-field experiment called SAND. And she's in my group, actually, in the red detection group, and research interests are in high energy cosmic neutron backgrounds and looking at scintillators, which she'll maybe explain here in a second. So Felicia, please take it away.
Thanks, GP, for the introduction. I'm going to try to share my screen. So what I'm going to be talking today actually is not related to my dissertation or my but this is something that I recently worked on. So let's see. I cannot move this part.
Nothing from nothing leaves nothing. You gotta have something if you want to be with me.
I tell you that the world we know is only less than 5% of the known universe? You, me, trees, planets, we're apparently only a tiny fraction of the universe. The rest of it, they are called dark matter and dark energy. Dark matter does not absorb, emit, or reflect lights, and therefore to our eyes, they look invisible. Yet we know they exist because of the effects they have on objects we can see directly. For many, many years, we have been searching for dark matter because we know that understanding dark matter is important to understand the size, shape, and future of our universe. And arguably, their existence may signify the rise of a new era of physics. No experiment so far has found evidence for their existence, except one. This one experiment is called Gamma Libra. And about 20 years ago, they made a huge controversy by uniquely claiming evidence for dark matter existence, while others have found nothing. This mystery has baffled and thrilled physicists for more than 2 decades. I am now searching for an alternative explanation for the observed Gamma Libra signal. Gamma Libra searches for dark matter by looking for tiny flashes of lights that are caused by dark matter slamming into atomic nuclei in their detector. The rises and falls of this signal should follow an annual pattern, and as the argument goes, this is because of Earth motion through stream of dark matter as we orbit the sun. Now, Gamma Libra observes this modulation. However, this modulation is left unconfirmed by other experiments, including those that employ the same detector material as Gamma Libra. They have not seen this modulation. So the question we want to ask is, well, are there maybe other things that could also produce tiny lights in this detector that are just somehow more pronounced in the Gamma Libra setup? So in the lab, I explore potential probes that may produce such signal. I have this material similar to the one used in the Gamma Libra experiment, and I expose this material to UV light, red light. I also plan to introduce variation in temperature and pressure. And to summarize the results so far, I seem to see several probes that may produce such signal in this detector. That said, more testings need to be done to test its reproducibility. If I manage to find these probes, it may shed some light on the world's most controversial dark matter signals. But if not, it is still a significant result because I help to rule out possibilities that may seem viable, narrowing the window of search, and that may help us to understand nothingness observed by many dark matter experiments a little bit better. Thank you.
Yay, that was great. Thank you. All right. So, yeah, I feel this one because Gamma Libra has been a thorn in the dark matter side for decades.
Yeah, for more than 2 decades now.
So maybe I'll start with asking, like, how did you get interested in this particular project, this particular science?
Yeah, it was really just taking opportunities as you were reading my introduction, and as you read, like I was working on Neutrino stuff when I was a graduate student, and then I joined the group, and then I don't know if you guys can listen, but those are my dogs. I'm sorry. But when I joined Livermore as a postdoc, I was offered to join this project because at the time I was thinking to do more of experimental work. And then I did not know much about dark matter when I first joined this project, but when I joined the project and I learned more about it, then I get interested in it. So sometimes you get interested in a project after you join the project.
Nice, nice. So I see one question here in the chat from Amani. Can dark matter or tiny flashes of light be observed in everyday life?
It's difficult because of the backgrounds, but yes, you can. Well, we are still trying to find evidence for their existence. We see tiny flashes of lights in this material, in this detector, but at this point, we're not sure yet if they actually correspond to dark matter interactions or not. People are still trying to put limits and then like improve these limits as we go along.
Nice. So Helena asks, how big is dark matter compared to an atom? And do we even know relatively how big it might be?
Compared to atom, in terms of, so there are several dark matter candidates with varying mass. So at the time, we're not sure yet. There are many candidates, but it's comparing to atom, I guess we're not sure yet at this point. It's still a big mystery.
Okay, thanks. Angelina asks, how many dark matter detectors are there and how big can they be?
Oh, there are many. There are many, and some of them can go to like, I think last is like ton scale, a few ton scale, like really large detector. They are also, I think, detectors that are like smaller in size. Like several people are using, like, for example, like Mars detector is only like a few ton, not a few ton, but like very small scale, and then like just like put it in like this alley in Oak Ridge National Laboratory. So it could range. It could range really greatly from very small to really large.
Nice. Mani also asks, how was the idea of the existence of dark matter discovered, and if now it is trying to be proved? So how do you know it's there?
Sorry, I lost the connection just now.
Oh, no worries. I'll read it again. So how was the idea of the existence of dark matter discovered, if it's now being tried to be proved? Like, how do we know it's there if we're looking for it?
Yeah, I guess we first see it because of we see light bands. When you have like concentration of mass, you can see that the light bends, and that's how I think we think that there is something there, but we cannot see it. It does not emit reflect light, so we cannot see it by eyes, but we can see the effect that they have on light source, but it bends.
Yeah, the other ones on the if you look at galaxies and look at how stars orbit galaxies, they're moving way too fast to be gravitationally bound in the galaxy.
Yes.
Yeah, we see tons of evidence, but it's all indirect. Yeah, it's all through how it moves stuff around.
Mm-hmm.
So maybe can you explain a little bit about how, where you might have to put these detectors, or what the backgrounds might be that make it hard to see these small signals?
So this is like very tiny flashes of lights, this detector. So you have to shield it from the radioactivities around it, and also from the cosmic backgrounds. So typically people will put it like deep underground with shielding around it, because you don't want to get light from radioactivities. You want to minimize your backgrounds to the best ability that you could. So they're typically located below ground, so that you get this these dirt above you that would shield you from the cosmic backgrounds as well.
Yeah, that's a very good point. I mean, people don't realize, like, there's so many cosmic rays or radioactive materials all around us just in natural life, and it's totally natural, but sensitive detectors are hard to see it. We have a question from Parasha. Do you think we could potentially develop a way to see dark matter? Like, see it? Like,
to see it, to make it reflect light so that our eyes can see it?
Yeah.
Interesting question. I guess, well, the property itself, it does not emit or reflect lights. So perhaps, I guess, like, at least like with a current technology, I don't think we can make them to emit light.
Yeah, we have to figure out how to like
lights. Yeah,
make it interact with something that does interact with light or something.
Yeah, you can probably do like second step, like you like probing it, like in a way, like we try to see it when it interacts with sodium iodide, or like with inorganic scintillators, and then you can see light when it interacts, but it itself reflecting lights, not sure. I would say probably you cannot, but at this point there are too many properties that we don't understand. Yeah,
we're still looking pretty hard for it. The more we rule out various possibilities, the sooner eventually it'll show up.
Yes, that's the hope. Yes.
Oh, and so there's Sarah mentioned, Angelina had a question I missed, which is dark matter necessarily a bad thing, as sometimes the media portrays? Like, I think it's got a negative name as dark matter. Like,
oh, because it's dark. The dark really comes because because we cannot see it with our eyes. But I can see how the word dark sounds negative.
Okay, great. Jessica points out here, we can see stuff with our eyeball, the detectors that we can't see with other types of detectors, or that we can use other types of detectors for. Detectors are needed to be able to see anything that we can't with our narrow vision right now. Okay, well, thank you. I think for now, let's move on to the next speaker. Thanks again, Felicia. That was excellent. And we'll have a chance if there's further questions later on when we do the roundtable. Next, we have Tomi Akindele. So Tomi is a research scientist here at Livermore. She received her PhD in nuclear engineering from UC Berkeley in 2018. And her dissertation was focusing on neutron emission from plutonium. And then prior to that, she received her bachelor's in nuclear engineering from Texas A&M in 2013. And her current research is on fundamental science for nuclear non-proliferations and safeguards. Take it away, Tomi.
Thank you for that introduction, GP. Okay, so nuclear reactors are the single largest source of carbon-free electricity per unit density of fuel. Energy is released from fission and not combustion, so you can power an entire city without releasing a single molecule of carbon dioxide. Unfortunately, nuclear reactors are also the single largest source of plutonium on Earth. And so we want countries to have access to clean, reliable electricity, but we don't want them to divert plutonium for nuclear weapons. So here's how antineutrinos can help. Antineutrinos are weakly interacting particles. So unlike neutrons or gamma rays, we can detect them on the order of meters, miles, even light years away from their source of origin. They're a direct signature of the fission process, so we can correlate their emission to the fissile inventory of the reactor core and understand how much plutonium is being generated in the reactor in real time. So over the past 20 years, researchers at Lawrence Livermore National Lab have demonstrated this capability with a series of experiments. The only problem was that all of these experiments needed to be in close proximity to the reactor core to maximize statistics. And so to be in close proximity usually implies two things: cooperation and access. So what happens if you don't have access to the facility you want to monitor? What happens if you can't even get into the country? What happens to antineutrino monitoring in the far field? And so that's what the Watchman collaboration, for which I'm a collaborator on, is trying to address. So this detector, the Watchman detector, will be 25 kilometers away from an active reactor. And this reactor will give out 10 to the 21st antineutrinos per second. And of those neutrinos, we're going to lose a large fraction of them just due to the fact that we're really far away. So we're not going to see all the ones that are emitted. Additionally, the exact same property that allows antineutrinos to travel light years without interaction makes it really difficult for us to see in our detector. So of the 10 to the 21st antineutrinos that are emitted per second, we only see about 9 events per week. And so with this low interaction rate, our signal to background looks a little bit like this. It's not really ideal. So my job on the Watchman collaboration is I perform simulations to better understand our signal and our background, specifically focusing on our background. So I look for ways that our background might mimic our signal of interest. And then I find ways that I can reduce the background by doing cuts on energy, spatial reconstruction, and other parameters that are different from the signal. And so as a direct result of my work, we can clean up our background so that our signal to background can look a little bit more like this. But with a better picture of what your signal looks like, you can better verify that nuclear reactors are being used for the peaceful purposes of generating clean and reliable electricity. Thank you.
That was great. Thank you so much. Wonderful. All right, please feel free to put questions in the chat. Tomi, a lot of people, the neutrino is talked about in popular science fiction and such, but can you maybe describe a little history or how difficult it was to find the neutrino?
Yeah, so one of the problems with the neutrino is originally it was first discovered in beta decay. And so in beta decay, when they put detectors around a beta decaying emitter, they noticed that there was missing energy. And so neutrinos are extremely weakly interacting. So when they tried to account for this missing energy, they couldn't find it. And so when they were trying to propose a solution, there was always this concern that maybe energy is not conserved. And we all know that energy conservation is like the most important fundamental thing that you'll ever hear about when it comes to science. And so someone proposed, I think it was some Poly, I forgot what his first name was, but there's this particle that carries energy that's weakly interacting and has very little weight. And so that's why we're not going to see it. And over years, we were able to use nuclear reactors to actually detect antineutrinos. And so we now know where this missing energy is. And so energy conservation is saved. Hooray.
Yeah. I think it was like, what, 30 or 40 years from prediction to actual detection.
Right.
For a long time. So we have some questions here. So Helena asks, how do you clear up the backgrounds specifically? Can you go into detail?
Yeah, so when we're looking for antineutrinos, we usually look at coincident events for a neutron-positron pair. So by looking for a pair of events that from antineutrino interaction, that really helps us to reduce a lot of our backgrounds, because when we have single events that are occurring in the detector from the radiation in the detector, the radiation from the water, cosmic muons coming from the sky, all these other things, we can help to reduce a lot of those backgrounds. And another important thing that we do is we have this really large tank of water, right? It's 20 meters in diameter, so it's a kiloton. So what we can do is we can actually make sure that all of the events that we're looking at occur right in the center of the detector. And so when they occur in the center of the detector, that's most likely to be from an antineutrino, because those events happen all over the detector. There's no spatial dependence on where that's interacting. Whereas your radiation is coming from the structural materials. And so those tend to be on the peripheral of the detector. So by forcing yourself to have a very small constraint on where these events are happening, you can remove a large amount of these backgrounds.
Yeah, and one quick thing. So can you describe what beta decay is? Some people may not have heard that term before.
Oh yeah, so beta decay is whenever you have so if you've ever stared at the periodic table for a long period of time, like I used to do in chemistry class, you'll notice that as you go up in proton number, you're gonna have a lot of neutrons. You have more neutrons with all of those protons to combat symbolic repulsion. So in a nuclear reactor, when these isotopes break apart, really heavy isotopes like uranium break apart, now each one of those fission products have way too many neutrons for the amount of protons that they're supporting. So they beta decay. And when you beta decay, you have a neutron that turns into a proton in the atom, and it gives off a antineutrino as well as a beta particle. And that's why we call it beta decay. And I care about the antineutrino.
Yeah. And it's an electron, right? The beta particle.
Right, a beta particle is an electron, right.
Okay, great. We have some other questions in the chat here. Valentina asks, what are some examples of the simulations you have done?
Right, so luckily enough, so Felicia is also on this call, and she was talking about another detector or another project, but Felicia has also helped out with doing fast neutron backgrounds. So I mentioned that there's these cosmic ray muons from the sky that are actually going through us right now, and they go through our detectors. And so sometimes they'll create these really highly energetic neutrons. And so that's something that Felicia has really been helpful in. Another background that I look into are radiation from the structural material. So everything is giving off gamma rays as they're decaying. And so I look into those to make sure that we can remove them. I've also looked into radionuclide production. So again, if you have heavy particles hitting water, sometimes it makes very weird things that also decay. And so we have to understand what those look like. And so really we've gone through and identified every background that we possibly could have from existing other detectors that have previously seen them. And we just simulate them in our detector using a simulation package called JOut4.
Nice. Another question from Amani. Instead of making the background more clear against the signal, is there a way to make the signal clearer instead? Can you boost the signal in some ways?
Yeah, so that's a really great point. And so one of the issues that we're having, because we're doing far field neutrino detection, is that we're so far away. So if we were closer, we'd have more signal. And that's one of the reasons why we first started out with these really close detectors. Another thing is actually changing the media. So right now, what I showed was Watchman for a water detector. And you could also use water-based liquid scintillator, or something called scintillator. And what that does is it increases the amount of light that's generated per interaction. And so when you have more light from the interaction, you can better see your signal because you can have smaller thresholds, which means that you can allow for more events that you would otherwise have cut out to look like your signal. And so changing the media or moving your detector closer, if you have that capability, is also another thing that you could do.
Nice. So Savannah asks, how do you ensure that the watchman doesn't pick up neutrinos from other facilities that may be in the radius that they could detect?
Yeah, that's a really great question because our single largest background is actually other anti-neutrinos from other reactors. And so one of the things that we've noticed is that where you actually put this detector matters. So if you put it in somewhere that has a really large installed nuclear capability, has a lot of nuclear power plants, for instance, France or places like China, then it's going to be very difficult to look for undeclared nuclear reactors. However, if you put it somewhere that there's not a lot of nuclear reactors, then you're not going to have as big of a background. And so there's also a lot of research that's being done into trying to do anti-neutrino directionality, where you might be actually able to pick out the direction in which these anti-neutrinos are coming from to have better pointing capability. But right now, that is our largest technological problem, is seeing anti-neutrinos from other reactors.
There's a follow-up for that one, actually. Just to clarify, this is to ensure that the countries aren't using nuclear engineering for developing weapons instead of just as a fuel source, correct? And then what would be different about the neutrinos from weapons versus fuel sources?
Right. So this is a very good question. And so I'm reading this again. Right. Okay. So so nuclear reactors, right? They're for clean electricity. And so one of the things that would be concerning from our standpoint is if someone had a nuclear reactor and never told anyone about it. Because if you're producing clean electricity, we all want to know, right? So if you're not telling people about these nuclear reactors, that might be a little concerning as to why you have it. And so one of the things that we're looking for is there a reactor there that we weren't told about? Another thing is nuclear reactors have very prescribed shutdowns and startup schedules, right? So every 18 months for traditional reactors, you're going to take your fuel out and you're going to put fresh fuel in because you've burned through that. Well, if you're shutting your reactor off and taking things out without telling other people about it, or doing it when it's not part of this prescribed schedule, that's also a little bit concerning. So really what we're looking for is behavior or patterns that are untraditional, because that's where we get a little bit concerned, and we might then look into other ways that we might ask, well, what are you doing? Why are you shutting your reactor off randomly? And then neutrinos from weapons and fuel sources. Without getting into too much detail about fuel enrichment, in general, the neutrinos, they're all going to be anti-neutrinos, and they're all going to react in the same way. Depending on what you're optimizing your nuclear reactor for, the anti-neutrino energy might be slightly different. However, in the detectors that I'm talking about, we don't have the capability because we don't have enough statistics. We have 9 events per week. We can't go into the nitty-gritties about what energy is this neutrino, because we're just happy to see a neutrino, right? However, some of these near detectors, they may have the capability of resolving the energy of these neutrinos, and the energy of these neutrinos might tell you information about how much plutonium or uranium is in your reactor, which might be able to help you understand if they're being used for weapons or electricity.
There's one question I skipped here, which was from Angelina. What inspired you to do this particular project? And when do you think this can be used as a more eco-friendly way of powering electricity in the future?
Yeah, so I don't want to date myself, but I guess I will for this to answer this question. But I started college in 2009, I know, a million years ago. And at the time when I was a nuclear engineer, I was really interested in clean and reliable ways of producing power. And they kept telling us about something called the nuclear renaissance, where we're going to build all this nuclear power, we're going to solve climate change, it's going to be awesome, no more coal. And then 2 years into school, the Fukushima Daiichi accident happened in Japan, and nuclear power wasn't looking very good anymore. And so I was worried about job prospects, and that's where I started thinking about what else can I do with this nuclear engineering degree. And so one thing that we learned was that there are going to be two problems that, regardless of what happens to nuclear power, will always exist. And that's going to be nuclear waste, like how do we get rid of this stuff after we burn in our reactor, as well as non-proliferation, right? Now that we know how to make nuclear weapons, this is also always going to be a concern. And so I got really interested in non-proliferation. And so that's how I kind of got involved in this project in this field. So, yeah.
Okay, I think we have one last one, then we can move on from Savannah again, which is, do you think countries might position extra facilities to hide particular facilities as a possible way to create more background?
Yeah, that's a very interesting question. And one of the concerns with that is making a nuclear reactor or building a nuclear reactor facility is not very easy. And so luckily, if you're building more reactors to hide this signal, it's going to take you a long time. However, that goes back to the anti-neutrino background, where if you already have a large installed nuclear capacity, just build another one, right? Because it wouldn't be an ideal location. So yeah, that's really great thinking. Yeah.
Okay, great. Thanks. I think we should probably move on. Thank you again so much. So the last speaker for this morning is going to be from Sarah Sandersholtz. So Sarah is a postdoctoral research in the Biosciences and Biotechnology division at Livermore. She's originally from Southern California, did her BA in chemistry and mathematics from Lewis and Clark College, and a PhD in chemistry from Stanford. She's very interested in research topics at the intersection of chemistry, biology, and computation. So Sarah, please take it away.
For the introduction. Okay, let me pull up my slides.
(50-50) on the audio for the song.
Yeah,
it's pretty good.
Sorry about that.
No, it's all good.
I'm not sure the SAGE attendees would recognize the song anyway. It's a little bit dated, but it's a good one nonetheless. Okay. Now it's
Okay, we see your front page now.
Can you see it? Okay, it started playing the music on my end, and so I didn't know if that was audible to everyone else, but I'll go ahead now. If it can advance. Okay. I have some good news and some bad news. The bad news is that there almost certainly will be another pandemic during our lifetime. The good news is that the next pandemic doesn't need to be as devastating as this one has been. If we could discover therapeutics to treat a new disease within weeks of the emergence of the virus that causes it, rather than months, we could save thousands of lives. This won't be easy, but it could be possible. Developing new drugs is like shooting darts at a dartboard. The darts are the drug compounds, and the board is one of the proteins that makes up the new virus. The bullseye is what you're aiming for, the drug target, or the part of the protein that will react with the drug to change the protein's function so that it doesn't make you sick. Running an experiment to test if a compound is effective is like throwing one dart at the board. In a typical game of darts, there's a single board with a single bullseye. Your target is obvious, but with drug discovery, it's not so simple. There are multiple boards, each with multiple bullseyes. How do you know where to throw your dart? Now you could use brute force and throw a dart at every bullseye on every board, but that would be time consuming and expensive. What if there was a way to narrow the possibilities? Imagine if you knew from the beginning that you only needed to try hitting one or two of the bullseyes on each of the boards. that knowledge would save you a lot of time and effort. My research aims to do just that. We've taken publicly available experimental data of protein structures and run it through an in-house structural modeling program, which predicts which parts of SARS-CoV-2 proteins will bind with which small molecules. Using clustering techniques from data science and cheminformatics tools, I've developed an automated computational procedure to analyze the patterns of binding in our modeling data. Based on those patterns, my pipeline identifies relevant binding sites in SARS-CoV-2, as well as the site-specific core chemical components involved in binding. From my results, I propose 2 simple rules of thumb for which binding sites will make more effective drug targets, which will help us prioritize our DART shots. The more similar the structure of a SARS-CoV-2 binding site is to the structure of binding sites in other viruses, the more promising it may be as a drug target. And the more drug-like the molecules that bind to that site, the more promising it may be. The process I've created can tell us both which bullseyes to aim for and how to design our darts. My approach is fast, relatively straightforward, and based on experimental data. And the best part is, my method is generalizable. We can apply it to any new virus as long as its genome sequence is available. Since it doesn't require expensive or sophisticated tools, you won't need special equipment to set up your game of drug discovery darts. So there's no need to take a shot in the dark when you can illuminate your target. Thank you.
Yay, thank you so much.
My pleasure. Thank you for having me.
Yeah, so folks, let's think about some questions. I have one. Just how do you get the inputs? How do you get those shapes like into your program? Like where do you find your inputs for the various viruses?
So we take experimentally measured crystal structures from Protein Data Bank. So this is a publicly available database that has 3D coordinates for proteins coupled with a small molecule or a peptide ligand that binds with it.
Nice. Okay. We have a question here from Amani. How do you predict when another pandemic will occur? Oh boy.
Oh, that's a very good question. And maybe a little bit outside of my area. The tool we're building is more of a rapid response tool. Like once we know that there's a pandemic, we could apply this to try to more quickly discover effective therapeutics. But you're onto a good question and a good point. In other areas of the lab, there are groups working on threat detection, and kind of monitoring different genomic sequences kind of in the environmental samples and trying to predict which of those might turn into a pandemic. So a little outside of my area, but other people are working on that.
Nice. So Helena asks, what programming languages do you use for this simulation?
Primarily Python.
Python is really useful for everything.
Yeah.
So Malak asks, and apologies if I mispronounced that, how long would it take to find the right targets from the start of a new virus?
So our computational pipeline can be run in less than a week, like a matter of days, once we have the experimental data that we need. The portion of the process that would take longer would actually be doing the experimental validation. So our tool kind of predicts certain sites that might make good drug targets, but of course, that's only a prediction. We need to test it in the lab, and so doing those experiments would probably take longer, maybe weeks to months.
Makes sense. Parasha asks, have you used this simulation on other viruses?
We are working on it. We originally developed it for SARS-CoV-2, but recently we've been applying it to the Nipah virus and the MERS virus, and we're actually also working on applying it for a few human proteins that play a role in cancer development.
Nice. Angelina asks, did your models or techniques help scientists develop a vaccine when COVID-19 was still super infectious?
I wish. We were a little late to the game. So this has been kind of a retroactive development using data on SARS-CoV-2. We weren't, in fact, I actually wasn't even at the lab at the time. I don't know if the project had started up yet. So we
wild
didn't have
that
the
it's been years.
opportunity for this pandemic, but hopefully we'll be ready for the next one.
Nice. Yeah, related question to that. So have you been able to use this to validate the fixes that we have right now, the vaccines that we already have? Like, we use that to validate your system that finds that particular target?
Yeah, in a sense. So there's structural data on the SARS-CoV-2 proteins with the vaccines and with the current drugs to treat COVID-19. And so to test our system, we actually didn't include that data in the data that we fed in to development, and we just compared with it at the end, kind of as a test case. And so we were able to identify those same sites. So that gives us some encouragement that this would work in the future too.
Oh, that's great. So Prasha also asked, does this simulation work by identifying the weakest protein and changing those, or which does it identify?
So we can run our process on any of the viral proteins and identify potential sites on any one of those. Our process is more for identification and less about changing a particular structure of the protein, but that's where a drug would come in, and that drug protein interaction might affect the structure and function. So we can apply a few criteria, a couple that I mentioned at the end, looking at how similar the structure of a particular site is to sites in other viruses, and looking at the types of molecules that bind there. Those would be two criteria that we could use to kind of rank the list of sites that our tool produces.
Very nice. Yeah, one other question I had, do you guys utilize like machine learning for this, or is this something that the big data sets could be used for on this?
Yeah, we're doing a bit of it's not too complicated, but fairly simple machine learning, some clustering.
Okay. Very nice. Do we have any other questions? Okay, it looks like we've exhausted them all. So thank you so much, Sarah. That was fantastic. And thanks to all the speakers. So at this point, we're going to kind of just open it up. We have about 20 minutes left in the program here, and we're going to do kind of a roundtable. And I'll kick off. And if you guys have any general questions, questions just on career or other things, feel free to put in the chat. But maybe I'll start it off with and I'll just one by one call people to make it easier. Maybe Tommy, if you get us started, how did you get interested in the science you're doing in general? Like, can you maybe describe how you got interested in it?
Yeah. Sorry, there's a baby here. So in terms of non-proliferation, I kind of already mentioned that, but specifically neutrino monitoring, how I got interested in that was while I was in grad school. People from Lawrence Livermore National Lab came and gave talks about some of the research that they were doing. And I always thought it was interesting because when we look at anti-neutrinos from a nuclear engineering background, we always kind of ignore them because they're so weakly interacting that there's nothing that you can do with it. And so it was really funny to see that there was an entire program based off of a particle that we traditionally ignore. And I just got really interested in that and followed that for my research.
Nice. What about you, Sarah? What do you think got you really interested in your science?
For me, my education career path has always been one step at a time. So I didn't, imagine in high school that I would be a scientist, but I enjoyed my math and science classes coming out of high school. So I thought, I probably want to major in something in this area, and took a lot of different classes in college to explore, and ended up, enjoying those and choosing chemistry and math. And so it's been kind of one step at a time, just trying to follow my interests and do things that I enjoy. And that's led me here. And I'm really happy it has.
Great. How about you, Becca? What led you to where you are at right now?
Oh, a lot of happy accidents, kind of. So I went into undergrad thinking I was going to be like really into semiconductors. And then I took my first kind of solid state physics class, and didn't do well. So I was like, oh no, what material science am I going to like? Like, I don't want to do semiconductors if this is how it's going to be the whole time. And then I also started getting into ceramic science at that point, and that like clicked with me. Like, I feel like for everyone, there are some types of science that clicks with them, and then there's some that are going to be kind of painful. The ceramic science is my thing that clicked with me, and then I happened to have a really great professor in that field who was like, hey, would you want to do a PhD? He's like, I have this cool one on 3D printing ceramics. And I was like, wow, I didn't even know you could do that. Like, I'm in, let's do that. And then through another happy accident, saw one of my current principal investigators, so kind of like my boss for a project, presenting at a conference about glass 3D printing. And it was kind of another moment of like, wow, I didn't even know we could do that. I want to do that. And so now here I am.
Great, thanks. And Felicia, same question for you. How'd you get there?
It's also really just by chance. So when I was an undergrad, my major was actually chemistry because I wanted to go to med school. Oh yeah, sorry, it's also chemistry. I wanted to go to medical school at that time, and it just so happened that when I was a third year undergrad, I took this class, nuclear chemistry, suggested by my staff advisor. So it's just like, you know, in Berkeley chemistry, you have to take election class. You can take inorganic, organic, or physical or materials, and you can also take nuclear. I just happened to take nuclear class at that time. And then I really liked that class. The professor who taught that class also happened to be my faculty advisor when I was an undergrad. So every 3 or 4 months or so, I would talk with him about career path that I probably would be interested to take. And then he suggests me to, why don't you just try to go deeper into nuclear chemistry? But unfortunately at that time, the nuclear chemistry department was kind of like a bit dying in Berkeley. So he told me why don't you go to nuclear engineering department, and then try to do research it and see if you like it. Somewhere after that, I think I joined 3 different research groups in nuclear engineering departments, and one of them was radiation detection. And I thought I really liked what I was doing there. And then here I am now doing radiation detection.
Okay,
so
great.
Really just by taking opportunities.
So we have some questions in the chat now. So maybe I'll start with Sarah. So can you compare your experience in college to your work right now? How is that different?
Yeah, I guess college was a lot more structured in that you're taking classes. And I mean, I guess I still have, meetings at certain times that I need to attend. But it's a little bit different. And I think at the time in college, I hadn't yet settled on that I wanted to do theory and computation. So I was still taking a lot of lab classes and exploring a lot of different areas of science. And so kind of each step along the way, maybe I learned to narrow in and find more fine-tune what my interests were. So now my work's completely computational, but back in college, I was in the lab, like you might imagine, mixing chemicals and stuff. So that's one big difference.
Nice. Maybe Becca, do you have an answer for that one as well?
Yeah. So I think the big difference between college, both undergrad and my PhD, and here is that working at the lab is way more collaborative than either my undergrad or my PhD, but in the best way you can imagine. I know in high school and in undergrad, sometimes you dread group projects because I know I was the one who was always doing all the work on the group projects, so I didn't like them very much. But here it's you're given group projects with everyone who is just as passionate about these subject areas as you are and has so many different varied knowledge bases. You work with so many different experts when you're at the lab that it's the best group project ever. It's oh, if I run into a problem, I know I'm going to have someone who I can talk to about it and that they're actually going to be able to help me. So yeah, a lot more collaborative, and I really like that.
Nice. Toby, what are your thoughts on the difference between college and work?
Yeah, so I agree with what was said before. So I guess I'll try to say something slightly different in the sense that it's kind of this awkward feeling that now that I'm working is recognizing that you are a subject matter expert in a weird way. And I don't want to be extremely boastful, but I just remember when I was in college and they would like ask you really hard pointed questions, and half the time it's like, I have no idea, I don't know, and you're thinking about it. And now when you get asked hard pointed questions, you're so ingrained in the work and in the research, and you really have this really intimate understanding of what you're doing, that it's kind of trivial to answer a question. Like someone asks you like a hard pointed question and you're just like, oh, I know that. Oh, I know that. Like it just, I don't know, you just kind of become an expert. And it's a lot of fun to actually take what you've been taught in college and really, in not even just college, even in high school, middle school, and really get to apply everything that you've ever been taught to your everyday life. For instance, like I remember when I was in high school and they taught us matrix math. Does anyone, I feel like they even introduced this in middle school. And I remember thinking, this is really weird math. Why do I need to know this? And now I use it all the time. And so it's just kind of like I get to make the most out of every education opportunity I've ever had. It's great. So
Nice.
Yeah.
So I want to get through some more of the questions, so maybe I'll bounce around on the speakers. So one question from Mani is, why should I consider a career in science and engineering? Maybe from Felicia. What do you think?
Yeah, well, you should consider a career in whatever that you feel interested in. If you feel interested in engineering and science, that you should try to pursue that, I think. So when I was in high school, I was not interested in science. I was interested in architecture. I wanted to be an architect. And then when I went to college, I started taking science classes, and then I get more and more interested in it, and then I changed my mind, and then now I'm a scientist. So you should do whatever you think is interesting, and if it's science and engineering, you should pursue that. You should try to pursue that.
Yeah, that's a great answer. You're always allowed to change your mind.
Yes, I think like in college, people change majors, usually multiple times. Because then you are exposed to like these different classes, and then you develop interest in like this many different classes, and then like one of them probably would really click with you, and then you just go with it.
Yeah, that was the best advice I got, was to take broad classes early on and sample a lot of things.
I did the same when I first went to college.
Sir, do you have anything to add for that one, or a particular question on why choose a science or engineering career?
Yeah, a couple of things that I really like about it. It feels like doing puzzles all the time. So it just feels fun. And there's always something new to learn, which is exciting too.
Nice. What about you, Becca? What would you say to that question?
Yeah, I think most of what I have to say is echoing what Felicia and Sarah said. It's a new problem every day that you have the tool set to solve, and you just have to apply yourself. So it's a good career if you really like problem solving in these specific ways.
Okay, so I'm going to move on to the next question because we got a couple others. Angelina asks, if you weren't in the field of science that you are in right now, which other science would you have branched off into? What other things might you be interested in? Maybe starting with Tomi.
Oh, that's a hard one. Actually, I think environmental science. So again, when I was in grad school, I had the opportunity to take elective classes, and it's just interesting how you pick your major for undergrad when you're like 18, 17, and then as you get older, you realize that you're more interested in real world problems. And so I learned a lot about, like, for instance, like how buildings are designed and how building designs can have a huge impact on how like electricity is consumed, specifically for carbon dioxide emissions. And then they also showed about just when you like schedule your meetings, how that can have a huge impact on how much energy you consume based off of like daylight, etc. And so I really think maybe environmental like design or things like that. I thought that was a really interesting class, and I guess we all now see the writing on the wall about how climate change is an issue, and so doing more to kind of address that.
Great. Felicia, do you have an answer for that one as well? Like, what else would you might be doing? Like,
yeah, so like when I was majoring in chemistry, when I was an undergrad, I was actually thinking to go to med school. I have always been interested in biology. So if I'm not in engineering, I probably would be in biology.
Yeah, I should say one of the things I love about Livermore labs, a lot of the national labs, is there's so much research going on
Yes.
You can change careers in the lab as well. You don't have to actually go elsewhere sometimes.
Yeah, you can. It's very diverse. You can collaborate with many people in a lab.
So we have another question here, which is from Angelina. What does your typical day of work look like, and how many hours of sleep do you get? I'll start that off with Becca.
Yeah, so my typical day of work, usually getting into work around like 8:30, 9 a.m. Answering emails, which I feel like as soon as you get into even grad school, you're gonna feel the pain of emails. And then usually it's either working, I do a little bit of computational work. So sometimes I will have a more in my office working on simulations day, doing different writing projects that I have going. So that's another thing, as a scientist, you're expected to write papers and publish these papers so that you can get your science out to other scientists and make sure that they agree with what you're doing, agree with your conclusions and everything, and that you're helping the field of science, right? And then I also have days where I'll just be in the lab, either mixing my resins or doing the actual 3D printing, which are always my favorite days. But yeah, as for the sleep, I probably don't get as much sleep as I should, but it's not because of the lab. Usually I'm heading out of the lab around like 5:30. And then I usually just stay up too late on my own. So usually like 6 or 7 hours of sleep, not really enough, but
Maybe Sarah, if you want to answer that one, and maybe I'll add a little twist on it. What's your Manny also asked, what's your balance between work and social life?
Yeah, so a typical day for me, since I'm not doing hands-on lab work, my lab looks pretty much like a typical office. I'm on my computer, and there's still a variety of tasks though. You know, I might be analyzing data, making figures, preparing presentations to share my research, or writing up a paper like Becca mentioned, sometimes meeting with colleagues to talk about what we're working on. Those are maybe some of the primary uses of my time. And I need a lot of sleep, so I try to get 8 or 8.5 hours every night if I can. But I think, yeah, and I do try to maintain boundaries too between work and life, and enjoy other facets of my life outside of the cool science that I get to do.
Great. And so there's still some other questions I'd like to get through. We have one that's, would you say that your career degrees fully prepared you for your career? Let's start with Felicia.
I would say in my case, I think yes, because I'm like a little bit of unique case, because when I was a student, I was already in Livermore, and I was working on, so like I'm working on some anti-neutrino research, even though I'm also now working on some dark matter stuff. But when I was a graduate student, I was working mostly on anti-neutrino research. So as a student, I was kind of already used with this field of study, and then I continue as a postdoc and still doing like half of my work is still like on like very similar things. But I think like what you really learn in grad school is not only the science, but the perseverance, I think. And that's, I think, like what probably would be more useful for you once you once you become a postdoc and, you know, sign this.
Nice. Let's see here. We have a question actually from Savannah, which is more of a technical one, which is a question, maybe this would be good for Tomi. Detecting secret nuclear facilities, isn't the root cause really uncooperative countries? And why should we invest in the research versus diplomacy, maybe? Oh, you're muted. Can we unmute Tomi? Oh, no.
Oh, yeah. Savan, great questions again. Right. So I guess there's two concerns, right? In one concern, you have uncooperative countries, right? And then another concern is countries who appear to be cooperating who aren't. And so if we look at, I guess, the Bible for nonproliferation, which is the Nuclear Nonproliferation Treaty, almost every country has signed it except for a handful of countries. But for the most part, almost every country has signed it. And so one concern we have is you've signed onto this agreement, you're getting resources to support nuclear power, and then you're now trying to divert that for other means. And you are right. Science, like diplomacy, is really important. And so that's why there's also something called science diplomacy, where when you have conflicts with countries or external conflicts, another thing that there's been a lot of investment into now is getting the scientists to work together on joint exercises. And so when we propose these really large detectors, the range and standoff of them, like we mentioned, is really dependent on the region that they're in. So sometimes you would actually need to be located within the specific country. And so it could be that if a country is caught doing something that they're not supposed to do, that you then, as part of a treaty or bilateral agreement between two countries, say, hey, for us to have trust in you, we need to do these joint exercises to verify that you're not doing other illicit activities. And so science diplomacy is also something that can be done. And so this is both using science and diplomacy at the same time. And I hope I answered that question without rambling.
That's great. That was great. So we're kind of close to the end of the time. So I just want to have one general question, which is, what do you guys like to do for fun? Like, what is something, I've heard, Becca, you like glass blowing, but do you have other hobbies or other things outside of the lab that you're interested in?
Oh yeah. So glass blowing, pottery throwing are two big ones. Really into video games because it lets me stay in contact. Also, having grown up on the East Coast, a lot of my friends are back on the East Coast. So video
You have
games.
a favorite one, like right now? Or?
Yeah, Final Fantasy 14.
Okay.
It's a massively multiplayer online game, so it's like kind of like hanging out with my friends in real life, but we can do it even though we're on different coasts. So that's really been helping me moving out all the way to the West Coast.
Nice. Sarah, what about you? What do you like to do for fun after work? Or?
Yeah, I really like to be active. So I like to play a few sports, volleyball, tennis, pickleball. I really enjoy the combination of using my body and my brain and kind of exciting my spirit all at once. It's a lot of fun.
Oh, nice. Do you know that is the volleyball back on site? Like, I remember we had the volleyball courts by Central Cafeteria. And
they have restarted. Yeah.
They have. Oh, interesting. Nice. Okay, Tommy, what about you? What do you like to do for fun?
Yeah. Oh, I was just gonna say, I really like going on hikes, and I will classify them into two categories. We have outdoor hikes where you can go out. We have so many national and regional parks that are really great in California. And then I also like what I call urban hikes, where I'm really just hiking from store to store. And so that's also a lot of fun too. And walking burns calories. And then I also, like buying new shoes and handbags. So one of the perks of the job is the fact that you can really buy things you don't need. So keep that in your mind. Yeah.
Okay, Felicia, what about you? What do you like to do for fun?
I'm a very indoor person. I like to just stay at home and draw. Sometimes I realize that I need to exercise and I would go on hiking. Very sometimes. Maybe like twice a month or something.
Nice, thank you. Okay, well, we're kind of to the end of the hour now, so I'd really like to thank all the speakers again for joining, and really thank the students and the SAGE campers. Thank you so much for coming out. We really appreciate you. Please look at the Livermore students. To get into college, you will have internships, and hopefully we'll see you in the SAGE program in the future. And feel free to reach out if there's any other questions you might have. Thank you so much.
Thank you, GB. Thank you, Joanna. And thank you to our 4 speakers. See you all at next SAGE Live. We'll be reaching out to you, and follow us on social media, Instagram, SAGE S Camp.
Have a wonderful weekend, all. It's like reverse popcorn.
All right, we're down to, oops, we still have a few. All
There we
right.
go. Yeah.
Awesome.
Oh, we lost Tommy. Oh, well. And Felicia.
Let's do a debrief. What went well? What
that was great. Yeah. Did Tommy and Felicia get booted, or did they actually just sign off?
I think they signed off.
Okay. No, I really appreciate. Thanks, Becca and Sarah. That was really helpful. Thanks, Jessica, for joining. Also, the support's always good. And for answering some of the questions in the chat.
It's one of the best Sage Lives I've ever attended. Very
Oh,
interesting.
good. I'm glad.
Very interesting. Yeah.
Like the talks were great, and they were really good questions. So I think I'm
Yeah, they
glad
were
we had
so
much better
engaged.
attendance.
Say again, Sarah.
Oh, just I was impressed with how engaged they were. Really good questions. And I thought the event was really well done. Thanks for including me as part of it. Really enjoyed the experience.
Sorry, let me stop recording.